Good evening, everyone. Today we will discuss nucleophilic addition reactions of carbonyl compounds. So, for example, aldehydes, ketones, they both have the common functional group that is carbonyl group. Since both of these classes of organic compounds have the same functional group that is polarized carbonyl group. So that's why they show a number of common reactions. So we will discuss it in detail. Look at the first molecule. This is your ketone, as in this carbonyl group is substituted with two alkyl groups, and the second one is aldehyde. In case of aldehyde, always carbonyl group is substituted with only one alkyl group. So, as this carbonyl group is quite polar due to the electronegativity difference between these two atoms, carbon and oxygen. So that's why here the carbon carries partial positive charge and oxygen also acquires partial negative charge. So being carbon carrying partial positive charge thus act as a good electrophilic center. Electrophilic center. So it is more prone to nucleophilic addition reaction due to its electrophilicity. And the electrophilicity is due to the difference in the electronegativities of both atoms. Difference in the electronegativity of carbon and oxygen. Clear? Yeah. Okay. As we know, nucleophile carries a negative charge. So it is attracted toward always positive charge species. That's why it will attack on this carbonyl center at the carbon. When nucleophile will approach this carbonyl compound, it will be perpendicular to this carbonyl compound. Here, the hybridization of carbon is sp2. When nucleophile is attacking at this carbon, there will be complete transference of pi electron that is toward oxygen. Then oxygen will acquire a negative charge and the bond between carbon and nucleophile is formed here as it is shown in this intermediate, and this is tetrahedral intermediate where the hybridization of this carbon is sp3. As you can see, in the reactant, the carbon is sp2 hybridized, and but in the intermediate, the carbon is sp3. Thus, the hybridization of carbon changes from sp2 to sp3, and a tetrahedral alkoxide intermediate is formed. Further, this intermediate will fix proton either from the solvent, maybe from water, clear, to give electrically neutral addition product. So this is all about the nucleophilic addition reaction, how nucleophile is going to attack at the carbonyl center, and further the oxygen, this oxide get protonated in the second step. So there are several reactions we will do with different reagents. In all of these, the mechanism is common. In first step, the nucleophile will attack, and in second step, it will the oxygen get protonated. Clear? Some of reactions are carried out in the presence of acid. But the question is why? Because in that case nucleophile is weak. If nucleophile is weak, then to proceed the reaction in further direction we need some acid. Clear? So what is the role of acid? Yes, in the presence of acids this oxygen of carbonyl group gets protonated. Like here, this oxygen get protonated and we get the intermediate one. Okay. Now, the positive charge on the oxygen increases. Due to increase in this positive charge on the oxygen, there will be electromagnetic shift from this carbon to this, which in turn makes this carbon more electrophilic in nature so that nucleophile can attack this carbon easily. That's why some reactions are carried out in the presence of weak acids. So here remember always the acid use is weak, otherwise if we will use strong acid, it will decompose this carbonyl compound. Mm. Moreover, the formation of carbon nucleophile bond is the rate determining step. So these are the characteristics of this particular nucleophilic addition reactions. You can find out the rate of reaction from the first step in which nucleophile attacks. So secondly, as the oxygen can acquire negative charge that facilitates a nucleophile attack. So these are all the characteristics of nucleophilic addition reactions. Then let's discuss the relative reactivities of aldehyde and ketones, and both of them have common functional group, that is carbonyl. This is your aldehyde. You can say it formaldehyde because in this carbon is substituted with two hydrogens. That's why it is named as formaldehyde. And this is your substituted aldehyde, and this is ketone. Out of these, which will be more reactive towards nucleophilic substitution reaction, in which the nucleophile will attack at fastest rate? Clear? So, the ease with which a nucleophile attacks on the carbonyl group, it depends upon the nature of substrate, whether you have chosen what kind of aldehyde or ketone. Clear? So, how the substrate affects the rate of reaction? Look at this carbon. This carbon is attached with one hydrogen, and this is your another hydrogen. Clear? But in second case, the carbon is attached with one alkyl group, where alkyl groups have plus I effect, that is known as inductive effect. In inductive effect, the alkyl group releases its sigma electrons towards the carbonyl group. When this alkyl group releases the sigma electron towards this carbonyl group, it decreases the electrophilicity of this carbon. Means as here this is acquiring partial positive charge and oxygen acquire partial negative charge. When this alkyl group will release the electron towards this carbon, it will neutralize the partial positive charge on the carbon. So by decreasing its electrophilicity, its reactivity also decreases. So that's why the formaldehyde is more reactive than the substituted aldehyde. The same is true for ketone and aldehyde, and among these substituted aldehyde is most reactive than the ketone because here are two alkyl groups. Yeah. So the due to presence of two alkyl groups, the electron density on the carbonyl carbon increases in this case, and it has lower reactivity as compared to other two aldehydes. Clear? So it also affects which will react at more fastest rate. The second factor is steric effects. This is also considered as the one of factors when we talk about the nucleophilic addition reactions, because the nucleophilic addition reactions, these are used by several chemists to form drugs and synthetic compounds. Yeah. So it is necessary to know Why this, at in what time the reaction will complete? It totally depends on the reactant. The first factor was the inductive effect. The second is the steric effect. Steric effect, how bulky group is attached to carbonyl carbon. Clear? You just have to check the bulkiness of the group attached to the carbonyl carbon. Okay, just a sec. This is your formaldehyde, acetaldehyde, acetone. This is diisopropyl ketone. Clear? Means this group can be, you can represent it as CH, CH3, CH3. Then further it is connected to carbonyl group CO. Again, CH, CH3, CH3. So these two are same molecules. I have just represented this in the open form. Okay. So by looking at this molecule, we can say that the fourth one is more bulky in nature because it is attached with larger groups. And the third one is less bulky. The second one is also less bulky. The first one is not bulkier in nature, not nature. So that's why the formaldehyde is more reactive than other aldehydes and ketones. Clear? So as the number and the size of these alkyl group increases, bulkiness increases. So the attack of nucleophile becomes more difficult at this carbonyl position. So steric hindrance reduces the rate of reaction. Steric hindrance lowers the reactivity of reactant. That may be substituted aldehyde or ketone. Clear? Okay, so this was all about the nucleophilic addition mechanism and the relative reactivity of aldehydes and ketone. Thus, we are moving towards the addition of water molecule. This is your first nucleophilic addition reaction. Here, the nucleophile we have been using is OH negative, and the source of OH negative is the water molecule. So as I have discussed the nucleophilic addition mechanism in generalized form, where first nucleophile attacks at the carbon and these pi electrons get shifted towards the oxygen. Clear? Thus forming an alkoxide. Here, the oxygen will get negative charge. Further, this molecule get protonated as the water also have the H positive ions. Thus, we will get the final product in which there are two hydroxy group attached to this carbon. This is your hydrate. The product is known as hydrate because this is hydrated. So same question, out of these, which is more reactive towards the nucleophilic addition of water? The answer is formaldehyde as compared to acetone. Clear? This is more reactive. If we have taken the reactant in which this carbon is substituted by three chlorine groups, clear? So in this reaction is occurring at more fastest rate. Why? Because after on the completion of reaction, these chlorine groups are stabilizing the hydrogens of the OH groups. In first step, what happened when OH negative will attack here? Then again alkoxide is formed. Upon formation of alkoxide, I am just drawing the your O negative H OH. Okay. Then this will get protonated. Then as chlorine is electronegative in nature, it will form the hydrogen bonding. And this chlorine will also form hydrogen bonding. So this is a stable product. That's why this is more reactive. Clear? Because of this carbon is more electron deficient in nature. The electron density on this carbon is less due to the electron withdrawing nature of these three chlorines. When these chlorine pull the electron from this carbon, this will further pull the electrons from carbonyl carbon, and this center will become more deficient. That's why this molecule is much more reactive than these two molecules. Okay. The second reagent is hydrogen cyanide. Okay. Hydrogen cyanide is less reactive in nature. So that's why this is a reaction that is catalyzed by a base to get cyanide in nucleophilic as nucleophile. We need the base to facilitate its formation. So here OH negative will abstract the H positive from here, and this carbon will get negative charge, thus facilitating the formation of Cn negative. So Cn negative is acting as nucleophile, will attack on this carbon atom, and there will be electromeric shift. And further, here is the formation of tetrahedral intermediate, that is alkoxide. Then further, this oxygen picks the proton from water or either solvent we have been using here. Then the final product is formed when the carbon is linked with one hydroxy group and another is cyanide. Then the product will be named as cyanohydrin. Clear? Yeah. So practically the pH should be between 9 to 10 because too much basic conditions cannot be used. If the more basic condition will be used, then the base itself can attack on this carbon. So it should be slightly basic just to facilitate the formation of Cn negative. Yeah. Okay, so here is your methyl group. The reactant we have chosen is acetaldehyde, and the product we will get is acetaldehyde cyanohydrin. When the reactant is chosen acetone, here are two methyl groups are present, then the product we will get is yeah. Then the product we will get is acetone cyanohydrin. So the name of product is depend upon the what kind of reactant we have been choosing. Clear? So in case of acetaldehyde product, what we will get is acetaldehyde cyanohydrin. On other hand, acetone is reactant, then the product is acetone cyanohydrin. Okay. Then the third reagent is bisulfite. Here, sodium bisulfite. when it is subjected to react with the carbonyl compound, again, here the bisulfite is acting as a nucleophile over here, and there will be electromeric shift of electron toward oxygen, and you can look at this intermediate, the bond between carbon and sulfur get formed, and in the final step there is transfer of hydrogen. In this step there is proton transfer. Why in this step proton transfer takes place? Because of the resonance of the SO3 at group. So the driving force for the proton transfer from this to this is the resonance stabilization SO3 negative group. That's why proton transfer takes place. So this is your final product here. So this is your acetone, sodium bisulfite addition product. If the reactant is acetaldehyde, then the product you will get is hydrogen over here. Then the product is named as acetaldehyde sodium bisulfite addition product. So basically it depends upon the reactant. Yeah. So we have studied about three reagents. The first one was our water, the second is hydrogen cyanide, and third is sodium bisulfite. Now, the next is the most important reagent is Grignard reagent. What is Grignard reagent? Grignard reagent is a reagent in which magnesium is present as metal, and it is linked to halide group as well with a alkyl group. So in short, we call it RMGX, where X is your any halide. That may be bromine, chlorine, iodine, etc. Clear? And R may be any alkyl group, that is methyl group, and phenyl group, C2H5, ethyl, propyl, butyl, pentyl. So any kind of Grignard reagent can be used. It depends what kind of product we needed in the synthesis reactions and what kind of drug we have been synthesizing. Clear? So there is peculiar property about Grignard reagent, as in this the alkyl group carries the negative charge. The alkyl group carries negative charge when it is linked to any electropositive metal. Electropositive metals which have tendency to lose its electrons. When always alkyl group is attached to metal, it acquires negative charge, such as in methyl lithium. In methyl lithium, methyl carries negative charge and the lithium carries positive charge. But we are discussing about specifically to about Grignard reagent, then that is RMGX. Clear? So magnesium has valency of 2 and the halide has a valency of -1. Thus, if we look the total charge on this MgX, that is +1. So as RMgX is a neutral molecule, then there will be a -1 charge on this alkyl group to neutralize the molecule. Thus, alkyl group carries a 1 negative charge. So this alkyl here acting as a nucleophile will attack on the carbonyl group, and further these pi electron get shifted towards oxygen, thus forming a salt. This is your tetrahedral intermediate where there is formation of a bond between this carbon and alkyl group, and this salt form O negative MgX positive. Yeah. Then in second step, this intermediate is hydrolyzed and this O negative gets protonated, plus with the formation of side product, byproduct, you can say MgOH Br. If X we have taken is Br, as water molecules have H positive, OH negative. Then this O negative get protonated, then OH negative will attach to Mg positive. Clear? Thus we get the byproduct MgBrOH. So this is your example in which I have shown the reagent CH3MgBr and the reactant is formaldehyde, and this is our final product in which there is formation of a carbon-carbon bond. So this was the reaction about the addition of Grignard reagent to carbonyl compounds. This is the most important reaction which synthetic chemists always use this reaction. The last one is addition of alcohols. Clear? So alcohol, how to identify alcohol in which there is presence of OH group. That functional group is identified as alcohol. When alcohol is treated with these carbonyl compounds, this OCH3, because here it is nucleophile, because there is partial. If we look at this molecule, as due to the difference in the electronegativities of oxygen and hydrogen, the oxygen carries partial negative charge and hydrogen have partial positive charge. So this methoxy group here is acting as nucleophile, then it attacks on the carbonyl electrophilic center. And further, as usual, nucleophilic addition mechanism, there will be shift of electron towards oxygen. Clear? Then when there is shifting of electron toward oxygen, this O negative will get protonated, then it form OH. Yeah. As this carbon is linked to one methoxy group. That's why it is called as hemiacetone, because it is linked to one methoxy group. You can say either alkoxy group. If there is another alkyl group you are using rather than methyl group, you can use ethyl, propyl, butyl. So for generalized term we use alkyl word, that's why you can also use alkoxy group. Clear? Further, this OH can also be removed from here. When this OH gets removed from here, again the second molecule of methanol is reacting to this hemiacetal, then forming the final product as acetal, in which the carbon is linked to 2-methoxy group. Clear? This is also known as ZEM dialkoxy compounds, because both of these methoxy groups are present at the same carbon. Clear? Okay. So next is, yeah, we can also carry out the reaction of aldehyde or ketone with the alcoholic group in which there are two OH groups are present. Then what will be the product in this case? In this case, there will be removal of one molecule of water, and the final product you will get a cyclic product, that is acetaldehyde, ethylene, acetal. Acetaldehyde, that is from your reactant, and ethylene, this one, and the product is acetal. Because in this, the both are acting as nucleophile. The first attack is by this on active, then there will be electromeric shift, then the intermediate will look like this: O CH2 CH2 O H H, O negative. Clear? Okay. Then in the second step, this O negative gets protonated. Yes. On protonation, it will form OH. Now, this OH is free. This can also attack on the carbonyl center, as again, this carbon is electrophilic in nature because it is further attached to the oxygen. And this is there is partial positive charge on it, partial negative charge, partial negative charge. So with the removal of OH group, then it will form a cyclic acetal. Clear? Here the OH is difficult to remove as OH negative because OH negative is a bad leaving group. So OH negative here is removed in the form of H2O positive. What is happening? This OH is linked to carbon. Let just I am drawing this mechanism in short. It will get protonated. Upon protonation, it will turn into OH2 positive. Here, the OH2 positive act as a good living group because the oxygen cannot reside the positive charge on it. So to neutralize itself, it will leave the carbon atom. Clear? Okay. So when I have chosen the reactant acetone, clear? Then same mechanism is followed in this case also, and the final product we get is acetone ethylene acetal. So the difference is in the above reaction, the reactant is acetaldehyde. The product we are getting is acetaldehyde ethylene acetal. When we replace the reactant with acetone, the product is acetone ethylene acetaldehyde. Clear? So this was the all about uh, nucleophilic addition reactions to carbonyl compounds. Clear? In these reactions, the nucleophile is added to carbonyl group. But in next lecture, we will do the nucleophilic addition reaction with the elimination of water molecule. Clear? So if you guys have any kind of query, then please ping me in the comment section and you can ask any kind of question regarding nucleophilic substitution reaction to carbonyl compounds and any other reactions in organic chemistry so that I can help you. So thank you.